Okay, ladies and gentlemen, last time we discussed Boolean circuits, and also we saw how a Boolean circuit can compute a Boolean function. So we defined the closure of a Boolean function set. So this is to be read as the closure, or sometimes functional closure of Q, where Q is just a subset of Boolean functions. So the closure of Q is just the set of all such functions you may obtain via a Boolean circuit. So there exists some C, which is a circuit, a Boolean circuit, a circuit over Q, where you take functions from Q as logical gates, as nodes, from which you assemble your circuit. There exists such a circuit that our f is just the function this circuit computes. Is this idea clear?
Yeah.
For example, you may compute conjunction via negation and disjunction. Let us give an example of such a circuit. If you take negation of x, negation of y, then you compute the disjunction of 2 and negate the result. Here you will take what? What will be computed? Here you will obtain not x, not y. At this node, it will be not x or not y. And here, not the negation of this previous disjunction, that is x and y. Is this idea clear?
Yeah.
And now we are interested in the following idea. How can one prove something about all functions you can obtain from Q? So how can one prove a property? Some property phi of all functions from this closure set. Apparently we have a comment. Okay, let me see. No, nothing interesting. Okay, how can we prove a property phi that takes place for every function you may compute from some given set Q? So the idea is something like that. Say, assume that you have just conjunction and disjunction. For example, these two functions, as they say, preserve one. So if we apply these functions to all unities, we will obtain a unity. Do you agree? It is obvious. But given our function is somehow constructed from conjunctions and disjunctions, is it true that if we fed it, if we feed it with all unities, we will obtain a unity? What do you think? It is quite intuitive. Look, if we have some circuit and we give it all unities, yeah, and here we have conjunctions and disjunctions somewhere, then we will obtain unity everywhere. Isn't it logical? Hmm? What do you think? Isn't it intuitively clear what I'm talking about? Ladies and gentlemen, is this clear?
Yes, it's clear.
So, and now I'm interested in the following question. Is it true that everything you may compute with a circuit that consists of just conjunctions and disjunctions, that every function you may obtain this way also preserves one, that is, when applied to the tuple of ones, it returns one? What do you think? Is it true or false?
True.
It is true, in fact, of course. But how can I prove it? What I'm doing formally? Formally, I'm trying to prove that every function from this closure set satisfies some property. For example, this one, it returns unity when given all unities. But let us analyze this situation abstractly. So we will prove the following lemma, lemma 1, which is about structural induction. Do you remember our induction business with strings from the fall months? From September, October, yeah? We started with this stuff, structural induction. Do you remember anything about that? No?
Yeah, not much.
So now we're interested in structural induction for Boolean circuits or Boolean functions. We may prove something. We may prove things about Boolean functions analyzing circuits which compute these functions. Okay. So what is given? Let Q be a set of Boolean functions, whatever. And phi be a predicate, a property. It is a predicate, something about Boolean functions, a predicate over this set of Boolean functions. Then, if the following holds, first of all, we have something like the base case. Every function from Q satisfies our property phi. Every projector, do you remember what projectors are? I have defined it last time. The projectors. Do you remember? But don't you remember? Yeah. What is a projector? A projector is a function that returns one specified argument out of its possibly many arguments. Is this idea clear?
Yes.
Okay, tell me please, what does this one return?
Why?
Why exactly? It's second argument. Okay, that is quite clear. And by definition, this bottom-like symbol stands for the set of all projectors, whatever. These are simplistic Boolean functions which return one of their arguments. It is quite clear. The set of all projectors. Okay. So if we are given some property phi, which is satisfied by everything in Q, by every projector, and the most important, this property is preserved by so-called superposition. Let us see if phi holds. Assume that we have some function f for which the following equation holds. Assume that for some function f we have something like that. So our f is obtained by applying h to the values returned by g1 and so on gm. Is it clear?
Yes.
Now assume that h satisfies our property phi. G1 satisfies our property phi, and so on. Assume that all these functions in the right hand side satisfy our property phi. Then assume that it is enough to prove that f satisfies phi. It is like the inductive step. So assume that all these are true. Is it clear? Then every function from the closure of Q, satisfies our property phi. Is this statement clear?
Yes.
Before proving it, let me give an example. So I'll prove that every function which belongs to this set preserves unity. That is, so I want to prove this statement using our lemma. So as an example, for each f, I can make my statement even stronger. I can also allow for implication here. If our function is computed using conjunction, disjunction, and implication, then it preserves unity. So if I give it as many unities as arguments it have, then it will return us unity. It will return us 1. By the way, for short, as a shorthand, I will denote this situation this way. Is this idea clear? So what is our property phi of f? What is our property? It must be a predicate. Some property of our function. Which one? What property I am proving? I want to make this situation similar to what I have in lemma 1. What is phi of f? Phi of f must be a property of a function. Some equation maybe, which this function must satisfy. Yeah? Ladies and gentlemen. Is it really too abstract for you? I don't think so. Please try harder. What is phi of f? What I'm proving about every function from clearly Q here is just the set of these 3 Boolean functions. But what is my property? Isn't it clear? You know, a predicate takes function and returns a statement. So I need a statement about f. Which statement? In which statement am I interested in? Oh no. It is just our equation. Is it clear now? This thing is either true or false for every given function. And I want to prove that for every function computable from conjunction, disjunction, and implication, this property will hold. Is it clear? Is anybody present now, by the way? Okay, we have sufficiently fewer students than we had initially, but okay. Is it clear? Hmm? So, if it is not, just ask your questions. So, I want to prove that every function expressible, computable via these three satisfies some property. According to lemma 1, it is enough to check these three things in order to do so. According to lemma 1, it suffices to check the following properties. Property 1. Every function from Q satisfies phi. That is, every function from our set here satisfies our phi. That is, f of all unities equals 1. Clearly, it is true. You know, 1 conjunction 1 is 1. 1 disjunction 1 is 1. 1 implication 1 is also 1. So that's okay. Property second. I need to prove that every projector function satisfies my property. So what do I need? That every projector, for every n, for every I, this projector function, when applied to all unities, gives us unity. But by definition, it returns its i's argument. And when all its arguments are 1, then it's clearly 1. Every projector preserves unity. And the crucial part is that if some function is obtained this way from functions preserving unity, then the result will preserve unity as well. It is also not hard to obtain. So what is given? It is given that some function is the so-called superposition of H and G1 to Gm. It is also given that H preserves unity. That is, given all unities as arguments, it returns 1. And also I have the same result for every function G. Gi of unities is unity. What is required? It is required to check that our function f also satisfies property phi. That is, it preserves 1. It preserves unity. Okay, let us see. What is f of all ones? What is it? According to the definition, it is h of g of 1 of all ones, and so on. But every function here preserves unity, so it is h of 1 of 1 of 1, while h also preserves 1, so it is 1. And the last point is okay. We have so far verified the base of our induction and the step. Hence, we may propagate this property phi from our initial functions to every function which is computable via circuit built from these ones. Is this idea clear?
Yes, it is.
Okay. So, what should we do now? We should prove lemma 1. In fact, we will reduce this structural induction to induction on natural numbers. But in order to do so, we need some natural parameter, something like a size of a function. And in fact, here we have a very natural concept of this size. Let f be a function which is computable, which belongs to the closure of Q. So you can compute it with a circuit over Q. There are many such circuits, maybe, but every such circuit has a size. And these sizes comprise a set of natural numbers. Let us take the least possible size of a circuit, computing f over q. The size of f will be just the least value, the minimum of the minimal size of circuits where C is a circuit, over Q, and C computes, that is, in our symbols, the function GC that C computes equals F. So it is just the least possible size of a circuit that computes F. Is this idea clear?
Yeah.
Okay, now let us return to our statement. What is given? These claims 1, 2, and 3 are given. And it is required to prove that every function f that belongs to the closure of Q satisfies property phi. I'll prove it by induction on the size of my function. So, in general, I want to prove that whatever function computable from Q satisfies phi. And I'll do that by considering sizes of this f. So, by induction, on the size of my function, and this is, of course, a natural number, so I have a legitimate induction. Okay. So, what is our inductive hypothesis? Our inductive hypothesis is as follows. For whatever function f prime computable from Q, if the size of this f prime is less than the size of our function, then it satisfies phi. So every function of less size is nice. It satisfies phi. Is it clear?
Yeah.
Okay. Let us denote the size of f by s. by the definition of size, we know that means that there exists some circuit of this size computing f. So let C be a circuit. Let C be a circuit over Q of size S. Of course, there exists one that computes F. Let us analyze this circuit. If you remember the definition of a circuit, you know that there are just three cases of what the last assignment of our circuit C may be. What is the last? Assignment of C. There are two cases that comprise a base and one which corresponds to the step of induction. Okay. The first case. In the first case, the very last assignment was of the following form. T assigned to be one of our input variables. Is this idea clear?
Yes.
So we have some inputs x1, xn, and the last assignment was t is xy. Okay. Our f is just the function that this circuit computes. But what is that? This function is just the projector. Is it clear?
Yes.
This assignment gives us projector, gives us a function that returns its i's argument. Okay. Ha! Now, look. Let us come back to the statement of our lemma. We know it is given that every projector satisfies property phi. Okay. That's enough. By our second assumption, every projector satisfies phi, hence our function f satisfies phi because it is just a projector. Is this idea clear?
Yes.
Okay. Second case, it is also trivial. It is when our last assignment was just something here. So we have already defined some variable ti and now just repeat it somewhere. Okay. Now f, which is g of c, is g c prime I. So it is a function that is computed by this prefix. You know, every prefix of a circuit is a circuit which is computed by this prefix. Okay. What about this function? What is its size? What is the size of its function, of this function? It is clearly it is not greater than the size of c prime I. Do you agree? You know, the
Yes.
size of the function is the minimal size of a circuit computing it. But this function is clearly computed by this circuit. it may be so that one can compute it in less size, but nevertheless, the minimal size, it is not greater than the size of this circuit. Is this idea clear?
Yes.
But this circuit is just a prefix of C. It is a proper prefix of C, so it is less than our S. But every function over Q, which is computable. By the way, this size is relative to Q, but for us, Q is fixed. Every function whose size is less than S is by the induction hypothesis satisfies phi. Okay. By the inductive hypothesis, we see that phi is true for this function, and hence phi is true for f because f is the same. And the last case, it is the only serious important case, is just like that. So we have as the last assignment, we have something like that: H, where H of course must belong to Q. H has been applied to some previously defined variables. So here in C prime, we have these variables already defined. Is it clear?
Yes.
Okay. But what is f? What is f? Our f is just h applied to functions defined by the respective prefix circuits. Very, very interesting, but it should be y I1 I am. Okay. Very interesting. Look, it is exactly this situation when a function has been obtained as a superposition. What is the size of function g, c prime, I don't know what, some j? What is the size? Its size is definitely not greater than the size of a circuit which computes this function. But this circuit is strictly less in size than our C. So the inductive hypothesis is applicable. It is strictly less than C, so the inductive hypothesis is applicable. By the inductive hypothesis, phi holds for all these functions. Is it clear?
Yes.
But what is H? H, according to our definition, H is something from our base set. But by our, according to our requirement 1, according to our assumption 1, everything in Q also satisfies phi. So we see that H satisfies phi, and every J satisfies phi. And F is the superposition. So by assumption 1, That means that phi is true for h. Look, phi is true for h, for all g, and also we know that f is just the superposition. So we can apply our third claim and obtain what we want, that phi of a holds. Is it clear? Do you have any questions? So this way, I have considered all possible cases of the last assignment of C, and in every case, applying the inductive hypothesis, I have proved that F satisfies phi. So our F indeed satisfies phi. Always. Is it clear?
Yes.
So we have obtained quite a universal way to prove that every function, to prove inductively that every function from the closure of Q satisfies some property. So it suffices to prove that this property is true for all basic functions, for all projectors, and also this property is preserved by superposition. Look, the statement of this lemma does not mention circuits. The proof is based on circuits, but the statement of this lemma itself does not explicitly mention circuits. Only here, of course, when we are talking about what the closure is. But in principle, there may be other ways to define closure. Okay, this lemma is very important, and it results in the following theorem: our algebraic properties of closure. Of these properties, most are obvious, and we have already discussed them in fact. For every two sets of Boolean functions, we have the following. First of all, every set is included in its closure. Second, monotonicity. If P is included into Q, then the closure of P is included into the closure of Q. And the last, most interesting one, the double closure of Q equals single closure of Q. Every function you may obtain using functions computable from Q is computable from Q itself. Is it clear?
Yes.
We have already discussed properties 1 and 2, but I'll briefly repeat the main idea here. So F belongs to Q. F is a basic function. So that means that there is a circuit computing this basic function. Clearly, there is such a circuit. You may easily construct it. Okay, let T1 be x1 and so on, Tn be xn, and then our last line, our last assignment is just applying f to T1, Tn. Clearly, this circuit computes f. Is it clear? I need to prove that every function from the base set is computable. Easily it is computable with this circuit. Do you agree? Is it clear? It must be clear. It is very easy. Okay. If P is included in the Q, then everything you may compute over P, you may also compute over Q. This must be obvious because every circuit over P is a circuit over Q. Just that. Just that. And the last one is the most interesting. So here we have set equality, which boils down to two set inclusions. To two set inclusions, two ways. Okay, this one is immediate, in fact, from our claim one, you know. Just see, every set is included into its closure. Hence, the closure of Q is included into its closure. The only thing we need, the only thing it remains to prove is this one. Everything in the closure of the closure belongs to the closure of Q. Ha! Let us rephrase it in such a way that we will have something like the conclusion of our lemma 1. Everything in the closure of some Q satisfies phi. Let us rephrase it this way. Okay. What do I need? I can rephrase it the following way. For every f that belongs to the closure of Q, the closure of the closure of Q, then f belongs to the closure of Q. So this is our phi. This is our phi. And this is our new Q. And this is our phi. Okay. What do I need? By lemma 1, it suffices to prove three things. First one, everything in Q prime, that is, everything in the closure of Q, satisfies phi. That is, everything in the closure of Q belongs to the closure of Q. This is, of course, trivial. The second one, about projectors. Every projector satisfies phi. That is, every projector belongs to the closure of Q, for whatever Q, of course. That means that every projector is computable over whatever basic set. Indeed, it is quite clear. In order to compute a projector, I can, for example, for the projector returning the its ice argument, I can take the following circuit: T s sine xi. That's all. This circuit computes my projector, and of course this circuit is a circuit over Q for whatever Q, because it doesn't use anything from Q from our base set. And what remains for us to prove as this our property phi is preserved via superposition. That is, assuming that our f is just a superposition of these functions, h, g1, gm, and so on, and assuming that all these functions satisfy phi, that is, all these functions are computable from Q, what I need is to check that f is also computable from Q. It is not hard to do so, but I should fix some circuits for these functions. So let D compute H, let Ci compute Gi. These are, of course, circuits over Q. So then I will construct a circuit for F. I will do it as a graph because it is simpler to catch the main idea here. And in order to express it accurately with assignments, we would require a little bit of formalistics, but nevertheless, it is not hard to do. So let us assign T1 to X1, X2 to T2, and so on. Now let us compute. Let us compute first all this G's. That is, we will put here, we will copy paste here our circuits for G's. Every such circuit takes all T's. We can copy T's here to the inputs of our circuits. Is it clear?
Yes.
And here we will obtain our G's. Here we will compute G1, here G2, here Gm. And then we will give all these things as inputs to the circuit D, which computes H. That's it. It is easy to see that this circuit computes exactly the superposition of H and G's. That is, it computes our F. And needless to say that this construction, where C's are circuits over Q and D is a circuit over Q, this construction is, of course, a circuit over Q computing F. Hence, F is computable over Q. Is it clear?
Yes.
Okay. And now we have tools to prove many obvious things formally. With these closure properties, we can, for example, prove equations between closures. For example, let us prove that everything which is computable via negation and conjunction is computable via negation and disjunction. Okay, what do we have? Clearly, negation is computable over negation and disjunction because Q is included into the closure of Q. It is quite clear. Also, we know that a conjunction is computable via negation and disjunction. You know, X and Y is just not X or not Y. And you can easily construct the respective circuit. So what? Hence, this set is a subset of what is computable via negation and disjunction. Now let us apply property 2. Let us apply monotonicity. The closure of greater set is generally greater. So we see that the closure of this set is included into the closure of this set. But applying property 3, the double closure equals single closure, we see that this set is included into this one. And similarly, one can prove that this set is included into this one. Is this idea clear?
Yes.
Another example is what we finished our previous lecture is. So that everything you may compute from the empty set is a projector. We know that every projector is computable from every Q. Here it is. Here is the proof. It is a circuit for projector. But you can compute nothing more other than projectors. So we shall apply our lemma 1 directly. That is, for every F, let us rephrase it. For every F, which belongs to the closure of the empty set, F is a projector. Okay, by lemma 1. By lemma 1, we should check 3 things. That everything from the base set satisfies our condition, but of course every function from the empty set satisfies whatever property. It is a vacuous truth. Is it clear?
Yes.
Second, every projector is a projector. Trivial. Is it clear? And the last one. If a function is a superposition of projectors, then it is a projector. So if it is a superposition of H and some G's, and we know that H satisfies our property. H is a projector, and all G's are projectors as well. Then, apparently, F is a projector itself. Let us check it. It is very easy. What is H? H is a projector, so assume that out of its m arguments, it returns some j's. Then, what is f of h, of x? It is h of these g's but h always returns its j's argument, so it is gj's of x. So we see that f equals gj's, while gj's is a projector. That's all. Is it clear?
Yes.
So as projectors are preserved by superposition, then we see that everything you may obtain from the empty set is a projector. But it is interesting which properties in general are preserved by a superposition. Let us look into this question. A set of Boolean functions P is called closed. It is called closed if and only if it equals its closure. What does it mean? That means that the set P is big enough to contain everything one can compute from it. So this set contains all functions you can obtain from it via programming, via constructing circuits. Is this idea clear?
Yes.
Now let us recall a few examples of closed sets we already know. The set of all Boolean functions is of course closed. It is obvious. Every function is computable from itself, or you may obtain it from theorem 2. And on the other hand, whatever you may obtain is a Boolean function by the definition of the set of all Boolean functions. So T is closed. In fact, the set of projectors is also closed. Why is it so? Let us check. Clearly, every set, in fact, every set by theorem 2, for every Q, for whatever set, Q is included into its closure. So there is no need to treat this fact specifically for any given Q. So the only thing we need is to prove that the closure of Q is included into Q. So this is obvious. Everything is included into its closure. What we need is proving that the closure of this set is included here. How can we prove it? In fact, by lemma 1, that is, everything which is computable from projectors is a projector itself. So by lemma 1, But this would require us to prove that every projector is a projector first. Second, every projector is a projector, they are identical. And the third claim will be exactly like this one. Exactly this one. That every superposition of projectors is a projector. And we have already checked it. Is this idea clear?
Yes.
Okay. Now let us construct more examples of closed sets. By definition, P1 is a set of functions that preserve unity, that preserve one. We are already familiar with them, in fact. So these are just such Boolean functions that, given all unities as the input, return 1. And similarly, P0 functions that preserve 0. If given all zeros, these functions return 0. Let us see some examples and then explore these two sets, or as they say in this area, classes of Boolean functions. We already know that conjunction, disjunction, and implication all preserve 1. Is it clear?
Yes, clear.
Does XOR preserve 1? 1 plus 1 is 1. Is it true? No, it is not. 1 plus 1 is 0. So it doesn't. What about negation? Is it true that not 1 equals 1?
No.
No, it is not. It equals 0. So negation also doesn't preserve 1. And what about preserving 0? Let us see. 0 and 0 is 0. 0 or 0 is, do you remember the truth table?
Yeah.
What is that? 0 or 0?
1.
Really? Disjunction.
Wait. 0.
It is 0. So that means that both conjunction and disjunction preserve 0. What about implication? 0 implies 0. Is it true or false? Do you remember the truth table? Don't you remember the truth table? It's a shame. From 0 it follows what?
0.
Everything. So it is true.
1.
Of course, it is 1. Hence, implication does not preserve 0. But on the other hand, 0 plus 0 is 0. Hence, XOR addition does preserve 0. And not 0 is 1. Hence, negation doesn't preserve 0. Is it clear? And my claim will be that both these sets are closed. So if you take a function, if you take the closure of the set of all functions preserving 0, what you obtain will be this exactly set. And likewise for computing 1. In fact, we have already checked it. But nevertheless, Let us repeat our arguments. Let us repeat our arguments. So, as usual, I need to prove just one inclusion, just this one. And similarly here. Why is it true? By lemma 1, I prove that for every f from the closure, f satisfies P0. As usual, I need three things. First, every function from the basic set belongs to P0. This is trivial. Second, every projector preserves zero. It is easy. Okay, let us take a projector. Let us give it all zeros. What the result will be? What is the result? Give all zeros to a projector function. Ladies and gentlemen, are you joking? What is a projector? Projector returns its ice argument. So now
0, 0, 0.
Zero, that's zero. So every projector, of course, satisfies our property. And the last line, our property is preserved by superposition. That is, if f is obtained from h and g's this way, and all these functions preserve zero themselves, then apparently it must be so that f preserves zero. It is also very easy to see. Let us give all zeros to f. Of course, you know, the zero with an arrow is just the tuple of zeros of respective size. So what do we have here? We have h of g1 of all zeros and so on, gm of all zeros. But g of all zeros is zero, so I will obtain h of all zeros, hence it is zero. All these properties are satisfied, hence we see that P0 is indeed closed. It is included, its closure is included into itself, hence its closure equals itself. Is it clear?
Yeah, yes. Yes.
Interestingly enough, an intersection of two closed sets is always closed. Let us prove this easy algebraical fact. Say, lemma 3. If P is closed and Q is closed, then the intersection is also closed. Okay, it's very easy. As usual, by theorem 2, it is immediate that intersection of whatever set is included into its closure. But now we are interested in the other direction. Okay, it is not hard either. P intersection Q is included into P. Do you agree? I hope you have understood what set intersection is. So P intersection Q is included in the P. Do you agree?
Yes.
Apply theorem 2, claim 2. Theorem 2, claim 2, that is the monotonicity claim. That is, the closure of a greater set is generally greater. Okay, let us do that. We have about 10 minutes still because we have started a little bit later than we should. So the closure of this set is included into the closure of P. And likewise, the closure of this set is included into the closure of Q. Ha! But you know, P and Q are closed sets. That is, this is just P and this is just Q. So we see that the closure of intersection is included into both P and Q. But if something is included into two sets, it is necessarily included into the intersection. That's all. A very neat, nice, easy algebraic argument based on theorem 2. So the closure of two closed sets is always closed. As an example, as a corollary, we see that the closure of the intersection of P0 and P1, the set of functions that preserve both 0 and 1, this set is closed. And we have conjunction and disjunction. Both they both belong to this set. But there are other interesting functions that belong to it. Do you remember the majority function? I presume you do not. So let me recall that the majority function is a very important object. The majority function of 3 arguments returns the value of the majority of its arguments. So if you have more zeros, it will give us 0. If you have more ones, it will give you 1. Formally, it gives us 1 if and only if we have more ones than zeros. Is it clear? Look, this function gives us 0 at all zeros, and it gives us 1 at all ones. Hence, the majority function belongs to P0 and P1. And whatever you may obtain from majority, conjunction and disjunction, everything you obtain this way will preserve both 0 and 1. Interesting. Another closed set of some interest is the set of self-dual functions. Let us consider this. Self-dual functions. First of all, let f be a Boolean function of an argument, say. Then we define the dual of f, that is f with this star, the dual of f. This function is defined the following way. It gives us the negation of the result that f would give us at its input negated. Is it clear? Or for short, we may denote it the following way: f of not x. Is it clear?
Yes.
As an example, we see that the dual of conjunction is disjunction. Why is it so? Easier. The dual of conjunction is by definition the negation of conjunction of negated arguments. So if we apply it to x and y, we would obtain this one, yeah, by definition.
Yes.
But we know that this is just disjunction. But what do you think? What is the dual of disjunction?
Intersection.
Conjunction. It is called conjunction.
Conjunction.
Of course. Why is it so? We can see it immediately. By definition, it will be not x or not y, but we know that this is just conjunction. And what is the negation of, what is the dual of negation? What do you think? What is it? This function, by definition, if we apply this function to x, we would obtain not of not x. Do you agree? According to this equation. But what is the triple negation? Not. What is it?
Not.
Aha. So we see that this function just equals its dual. The negation function just equals its dual. Interesting. And what about the majority function? Look, let us compute its dual. What is the dual of majority function? It is the negation of majority of not x, not y, not z. What is it? Let us compute it. Let's put it here. So it is the majority, the dual of majority. What is it? We have all zeros, so it is not majority of all ones. What is not majority of all ones? Majority of ones is 1 and not majority is 0. What do we have here? The negation of majority of 1, 1, 0. What is it? The majority of 1, 1, 0 is 1, so here we have 0. Next. not majority 101. It is clearly 0 here. Not majority 100. Here we have 0, not 0, 1. And so on. We see, in fact, that our dual to majority is the same as majority as well. Is it clear?
Yes.
That means that the majority function, that means that our majority function equals its dual. Interesting. One more thing to consider. First of all, let us observe that the dual of the dual is f itself. It is easy to see. What is the dual of the dual of x? By definition, it is not the dual of f applied to all the arguments negated. But here we have, what is this one? It is not f applied to all the arguments negated. So it is just f. Is it clear?
Yes.
We say that a function is self-dual if it equals its dual. A function is called self-dual if and only if it equals its dual. So we see that negation and majority are self-dual functions. And by definition, the set S is just the set of all self-dual Boolean functions. And I claim that this set is closed. Our last statement for today is that the set of all self-dual functions is closed. The closure, if you have a few self-dual functions, you may obtain just a self-dual function. If you have all self-dual functions, you will obtain exactly this set. As usual, S is clearly included into its closure, so I need to prove that the closure of S is included into S. As usual, let us apply lemma 1. So we need 3 things. So if we rephrase it, this will be as this one. Everything from the closure of S belongs to S. Yeah. So first of all, everything from S belongs to S. It is trivial. Second one. The second one says that every projector is self-dual. Let us see. So we're interested in a dual to a projector. We have taken a projector and its dual. What is it? It is not projector applied to not x1 to all our arguments negated. So it will be not i's argument. It will be xi, that is the same as the original projector would give us. Is it clear? So
Yes.
the dual of a projector equals this projector itself. And the last claim is to check that self-duality is preserved via superpositions. Assume that a function f is obtained from h and g1 to gm this way, and h and all these functions g are self-dual. Then I want to prove. Can you hear me?
Yeah, I can hear you.
Then I should prove that f itself is self-dual. It is as easy as usual. Let us compute the dual for f. What is it? It is not f of our arguments negated. But what is f? F is just h of g's. So I should substitute not x for x. There will be h of g1 of not x, and so on. But look, h equals its dual and g equals its dual. So let us replace h with its dual here and g. They are self-dual. So I can replace these functions with their duals. But what is dual of not x? Yeah. It will be not g1 of not x. And the same here. Not gm of not x. So it is just not. It will be not h, and here I'll take not 2 times, one from this star and one here. And I will apply this negations twice to this tuple. As a result, we see h of g1 and so on, gm of h here. It is just our f of h. Is it clear?
Yes.
That's it. So we have one more non-trivial and in fact very important class which is closed. The class or the set of self-dual functions. So far, our examples of self-dual of closed sets consist of self-duals, functions preserving 0 and 1. They are called collectively constant preserving functions. Various intersections. Of course, the set of projectors and the set of all Boolean functions. we shall add two more closed sets, and then we will be able to prove a marvelous, a very interesting result, which is known as Post's criterion, which allow us to say when a given set of Boolean functions, probably a finite one, is enough to compute every Boolean function. We shall explore these things next time. Do you have any questions? So apparently you have no questions. Thank you.